So hi everyone, my name's Daniel. I'm an Intercalated student, or I've just completed my Intercalated degree from University College London in London. And my project is about renal tract abnormalities in spina bifida. So I've tried to pitch this at a level, I know we're a very diverse audience, so I've tried to pitch it at a level that we're all on the same page. So if you'd like a bit more detail about the genetic techniques and stuff that I use, then please feel free to ask me afterwards. So I'm interested in everything that happens before birth, so developmental biology, from the time of conception up until we're born. And the condition, what happened to my, that's a real shame. Okay, so the condition I chose to study is spina bifida, and spina bifida is one of the most common birth defects. What happens in spina bifida is the spinal cord doesn't develop properly, and what happens is you get this open lesion on the baby's back, and that results in neurological deterioration. And I had a really nice picture of a baby here with spina bifida, but unfortunately it's gone. And one of the consequences, one of the most common consequences of spina bifida is a poor innervation of the bladder. And because of this poor innervation of the bladder, so this is the bladder here, it doesn't function properly, and this leads to kidney failure, kidney damage later in life. Now, a lot of the mechanisms of renal damage and bladder dysfunction in spina bifida are normally thought to occur after birth. But me and my lab have reason to suggest that these mechanisms might occur with spina bifida before birth in the womb. And the two reasons we think this are here, this is the first reason, that fetal surgery doesn't improve these outcomes in patients with spina bifida, i.e. when you operate before birth, it doesn't really make a difference to the bladder, it doesn't really make a difference to the kidney. And the reason I think this may be is because these problems occur before birth, before the timing of fetal surgery. The second piece of evidence that suggests that, or the second piece of evidence which leads me to think that these deficits occur before birth, is because in humans and in rat models of spina bifida, there's a reduced innervation in spina bifida bladders. So one of the most important things in spina bifida, or renal deterioration in spina bifida, is that initial loss of nerves in the bladder. So obviously my aim is very simple, to find out in animal models of spina bifida, i.e. the mouse, whether renal tract abnormalities occur before birth. So my method was actually very simple. So we used genetic engineering techniques to produce fetuses with spina bifida, and you can see one here. So this is the back of the fetus, there's its legs, there's its tail, and you can see the spina bifida lesion here. This is what the previous slide should have showed, or should have looked like. And one day before birth, so this is E18.5, embryonic day 18.5, I dissected out the renal tracts of this mice. So I dissected out the kidney, the bladder, and the ureter. And then I used staining techniques to analyze the renal tracts to see if there were any differences between those mice with spina bifida and the mice without spina bifida. So I had lots of different animal models to choose from because my lab is primarily centered on the mechanisms of spina bifida. And the model that I chose to look at were this model here, the grainy head-like gene model. And I chose to work with this model because the characteristics of the spina bifida lesion are very, very similar to the patient condition. So what we do with these mice is we manipulate the two, no, where's it gone? There we go, sorry. We manipulate the two genes, grainy head-like 2, grainy head-like 3, increase their levels, increase their expression, and this causes spina bifida in the mice. And this works because grainy head-like 2 and grainy head-like 3 are really important for spinal cord development. Now, what I didn't realize, and I only realize now, is grainy head-like 2 and grainy head-like 3 are also very important for renal tract development. So if I do open up my mice and I do see changes, I need to find out whether it's because of spina bifida or because I'm playing around with the genes. So I had 3 mouse models to work with. The first one I employed was increasing grainy head-like 3, and by increasing grainy head-like 3 in the fetuses, I caused spina bifida. And what I found in these mice is that their ureters were very strange. So some of the ureters were tortuous. I prefer to use the term wiggly, but I've told that's not sciencey enough. So I'll say wiggly. So some of them were wiggly, and some of them were dilated like this. And this really excited me because in patients with spina bifida, what happens is because urine accumulates in the bladder, it refluxes up and you get this kind of appearance. So I thought, fantastic, this model might be representative. Now, I needed to validate this by looking at the bladder to see if there was a reduced innervation, because I said this is the base of the lesion. And it really surprised me that when I looked at the bladder of these mice, what I found is that the innervation between spina bifida bladders and normal bladders was similar. So let me just explain this to you here. The green doesn't turn up very well, but green is muscle, okay? Blue is the nuclei, and red is the nerves. And this is a normal bladder, and this is a spina bifida bladder, and there is innervation present in the spina bifida bladder, so this confused me quite a lot. The second model I looked at was playing around with grainy head-like 2 levels, so I increased grainy head-like 2 expression, that caused spina bifida. And I observed in spina bifida mice this really weird kidney morphology. Now, I prefer to call these egg-shaped kidneys. Again, I told that wasn't sciencey enough. So they had this weird morphology. But interestingly, when I looked at histology, when I stained the kidneys and I cut them up and looked under the microscope, they look very similar. Okay, so it seems like the 2 animal models I've used aren't really representative of spina bifida in patients. So then what I did was something very different, in that in one model, the first model I showed you, I really highly increased the dose of grainy head-like 3. In the second model I showed you, I really highly increased the dose of grainy head-like 2. What I did with this animal model, I slightly increased grainy head-like 3 and slightly increased grainy head-like 2, hoping that that would cause spina bifida, but not cause the abnormalities I observed with the first 2 models, which likely occur as a result of the grainy head-like genes and not spina bifida. And interestingly, I saw a completely different defect. So what I saw is in these mice, again, this hasn't shown up very well, but the renal pelvis, oh God, that's really bad, I can't see it at all. The renal pelvis, i.e. the bit inside the kidney, is really dilated in those with spina bifida, but not those without. So this is all very confusing. What does this mean? So though all my 3 animal models had spina bifida, all of them had very, very different renal tract abnormalities. And I also showed you that the innervation of the bladders, i.e. the basis of spina bifida, it doesn't make sense in that the innervation is there. So it's unlikely that these models are representative of spina bifida. But what I did show is that if you slightly increase grainy head-like 2, there are no abnormalities. If you slightly increase grainy head-like 3, there are no abnormalities. But if you increase both at the same time, there are abnormalities. And this, as in the spinal cord and in the skin, suggests that grainy head-like 2 and grainy head-like 3 interact during renal development. And this is a novel discovery. So my conclusion is both exciting and miserable, in that I had a question, does spina bifida cause renal tract abnormalities before birth? And I didn't show that at all. What I did show is that the 2 genes, grainy head-like 2 and grainy head-like 3, do have very important functions during renal tract development. And that's all. So I had, just before I finish, I had 7 weeks and 2 days to complete this work. So I was really pushed for time, and I wouldn't have been able to do it without the help of my supervisors, Andy and Nick, and the rest of the team. I'd like to thank Kidney Research UK for all their support, and thank you very much. I'll take any questions.
Well done. Questions? Yep. John.
What happens to the expression of grainy head 2 and 3 in human spina bifida?
So this is the strange thing, because it seems like a really good model to study spina bifida, but the thing is, if you look at patients, their grainy head-like 2 and grainy head-like 3 levels aren't altered. And this suggests that there's a difference between species, but the reason we use that model is because the characteristics of the lesion and the effect it has on the mouse are very similar to the human condition.
So I may have missed this, but how do you raise the level?
Okay, so I didn't explain this because it would have taken me a really long time, but the grainy head-like 2 model is a naturally occurring model. I don't know if you read the...
It's an overexpression model.
It's just an overexpression model. So, and the second model we use, the grainy head-like 3 model, we've inserted a bacterial artificial chromosome containing intact grainy head-like 3. Yeah.
Jenny.
You said there was no difference in innervation in the bladder, like you had that staining for TUJ1, and you didn't show quantification. But I wonder, is there something more subtle that might be going on with the different types of nerves that innervate the bladder that you may have missed, and you actually may have a bladder neurology phenotype and you've missed it?
Absolutely, that's a possibility. One of the things I really wanted to test was to see if specifically the autonomic innervation was different, but unfortunately I didn't have time to do that.
Yeah, last question.
Is there a loss of all nerves in spina bifida, or is it specific to sensory nerves or motor nerves, or any particular nerve type in the bladder?
So as far as I'm aware, the deficit occurs below the level of the lesion. So say the lesion is mid-back, you'll get problems with the bowel, you'll get problems with the bladder, you'll get problems with motor function in the legs. But yeah. Does that answer your question?
Okay, another one for lunchtime discussion. So, thank you very much.
Thank you.